All right, hello and welcome to our final Omis115 project. This is Claire Zyfers.
I'm Yash.
I'm Matteo.
So for our project, we used MLB pitch data from the 2019 baseball season, and we want to use machine learning algorithms to determine the importance of pitch variables on the outcome of said pitch, and determine also how successful pitcher has been while providing the information players need to know to throw the optimal pitch. In a baseball game, the pitcher is arguably the most important position. They're the only position guaranteed to touch the ball in every play, so their actions and their decisions have a large impact on not only that at-bat, but consequently the rest of the game. Pitchers can use their data to see how effective their pitches are and the relationship between certain factors and the outcome. This could be monumental to track league-wide trends as well as tracking individual moments. While we isolated for a specific pitcher, John Lester, everything in our program could be applied to the data set across the board. This way, there's flexibility in tracking macro trends as well as tracking specific pitchers, requiring only a slight modification of the code.
Moving on to the data sets. For this project, we used MLB pitch data from 2019. Specifically, we used 3 different data sets, which are listed on the slide. The at-bats data set includes information such as pitcher ID and the result of the pitch. This would allow us to know if the pitch resulted in a single, double, strikeout, flyout, etc. The second data set we used is the 2019 pitches data set. This data set includes the bulk of the data, which we would use to analyze the individual pitches. As shown above, some of the columns that we looked at were useful, such as the speed of the ball, the amount of spin, the location of the ball entering the strike zone, and more. However, there were also many columns that we didn't need that we'll discuss later. The final data set is the player names data set, which matches player names, first and last, to their player IDs. Moving on to the cleaning. The cleaning / pre-processing of this project was relatively straightforward. The first thing we had to do was merge the 3 data sets into one data frame on pitcher ID. Next, we went through the 50 columns of this merged data frame and decided to remove the columns which were irrelevant in determining events or were ambiguous. The reason some columns were ambiguous was the data on Kaggle did not include some of the descriptions for some of the columns. We also had to change some of the values in preparation for our machine learning section. Some examples of what we changed were replacing the pitch type to numeric values, as well as simplifying some of the pitch results or events to be less confusing. For example, this means that we changed all of the different plays, which resulted in and out to out. Lastly, we dropped all the non-pitch related events, as these events are not relevant to the purpose of this project. For example, we dropped every event which was not a direct result of a pitch, such as stealing a base.
For our first machine learning algorithm, we wanted to use multinomial logistic regression because it allows us to predict the value of a multi-class variable like we have. As we talked about earlier, we cleaned our data and dropped unnecessary columns such as those that weren't quantifiable. We also adjusted specific columns to refer to a broader bucket. Since the end result of any kind of an out is an out, we made the above general buckets that you can see there. Our assumption was that it's not important whether it's a fly out or a ground out, but rather an out. And then we ended up with the events above. After doing our cleaning, our data set had roughly 63,000 rows and 29 features. To stay within the parameters of the project, roughly 1,000 to 10,000 instances, we decided to isolate for a specific pitcher. However, our following machine learning algorithms could be applied to the entire data set as well if you wanted to seek larger level macro trends and findings. Similarly, other pitchers could find their own data simply by putting their last name instead. After isolating for John Lester, we had a little over 3,000 pitches shown and still the aforementioned 29 features. Given that all our data was in float, we still had uneven numerical values, and to that end, we first made sure to scale our data. We initially used the solver mutant CG and let the function use the default tree parameter of 1.0. Our results were as good as we could have hoped, and I strongly believe that our assumption was correct in that placing all the event categories into distinct buckets would play a larger role in ensuring higher training and testing score. Based on the numbers, however, there is a chance that there might be some variance creating slight overfitting. However, we wanted to make sure that we were getting the best output from our program, so we wanted to tune our data, and we ran the program again with 3 different parameters. First, we decreased the sphere parameter 0.05. Second, we increased the sphere parameter 50. And lastly, we changed the solver from Newton CG to LBFGS. However, our findings were a little surprising. Even though we used the numbers above, we also tried other numbers. And regardless of how we tuned our parameters, our outcomes were always the same. We ran it repeatedly and with different numbers, but the output never changed. So one important thing we learned was that machine learning is unpredictable. We were surprised to see the same number across the board. It's such a complex field and requires a fundamental understanding to harness it properly.
Now discussing the KNN section. We used KNN largely as a different machine learning algorithm to compare to the logistic regression results. The reason we used KNN is that it is simple to implement. However, it is important to note that there are significant cons that come along with it. Since our data set is relatively large with 728,000 rows before cleaning, there is a high prediction cost while using KNN. As you can see, there is an overfitting problem with the KNN section. We attempted to fix this by using KNN tuning, but struggled with that section throughout the project. We couldn't manage to find the value of K with the lowest errors, so we used 5 as that is a common value to start with.
Okay, so moving on to the random forest machine learning. Random forests operate by constructing a multitude of decision trees at the training time and then output the class that is the mean prediction of the individual trees. So I first set K to 5, and K equal to 5 is the square root of the number of features. And when we did this, we got a test accuracy score of 0.65 and a training score of 0.97. So you can see that there were still major overfitting issues on the data set, despite having tuned this beforehand. And moving on to the data tree visualization. In order to visualize the tree and see what the likelihood that our chosen pitcher, John Lester, would throw a pitch, resulting in an out, I created a new binary column called event type in the data frame, and based on the event of the play. If the event was an out, it would be assigned a score of 0, and if it was any other event, such as a single or a home run, it would be assigned a 1. As you can see, after visualizing the tree, the parent node contains 3,028 total events, which is all of the pitches that our pitcher John Lester threw. And it also contains the split point of event type less than or equal to 0.5. If the event is an out, then it's less than 0.5, so it's sent to the left, and if it's not an out, then it's sent to the right. Therefore, in conclusion, Lester threw more pitches leading to outs. As you can see, he threw 1,969 pitches leading to outs and only 1,059 pitches leading to other events. And outs benefit Lester's teams while other events work against his team in the game. So because there's more outs, Lester can be seen as a beneficial team member to his team.
With our findings and our regression models with roughly 65% confidence, given the features, we can predict the outcome of an at-bat. In a sport where 30% is considered elite, our findings could have a real statistical impact on the game. And as mentioned before, John Lester has continued success in the league, as evident by the fact that his pitchers often lead to more outs than his pitchers that do not, which benefit his team overall.
While running machine learning, we found different key findings. So our first key finding was that while machine learning is incredibly powerful at some level, it's only as powerful as the user. Without proper knowledge and understanding of the concepts, the power of machine learning risks becoming mishandled. Our second key finding is that there is still quite a lot of data cleaning required for machine learning, which takes on additional time into an already confusing process. And our final key finding was that organization and clarity is key. We struggled with getting the same accuracy results on different machine learning algorithms, which could have been avoided with more pre-planning. And that is the end of our presentation. Thank you all so much for your time and watching this.